The sun rises every morning and sets every evening. This rhythm has structured human consciousness for as long as our species has existed. We measure time by its cycles. We orient ourselves by its position. We feel its on our skin and see its light reflected in everything around us. For this reason, the sun occupies a unique psychological position in human thought. It is not merely one object among many in the sky. It is the reference point against which all other celestial phenomena are implicitly judged. When ancient astronomers looked at stars, they could not initially measure their distances or sizes, could only observe that stars far dimmer than the sun, and that they remained in fixed positions relative to one another across the seasons. The conclusion seemed obvious. The stars were farther away, and therefore smaller or less luminous. The sun, by contrast, appeared supremely powerful, a source of energy so abundant that it warmed an entire world and sustained all visible life. To suggest that other objects in the universe might rival or exceed the sun seemed almost like heresy against the evidence of direct perception. This psychological anchor is difficult to overstate. Even as telescopes were invented and improved, even as measurements became more precise, the sun read its position as the cosmic reference object. Textbooks defined stellar properties in terms of solar units. Astronomers spoke of stars being 2 solar masses, or possessing 10 solar radii. The sun became the yardstick, not because it held any special position in the universe, it does not, but because it was the first star we could measure with reasonable accuracy. Its properties became the baseline against which all others were compared. To understand why this matters, we must examine the sun's actual characteristics with precision. The sun's diameter is approximately 1.4 million kilometers. This is an almost incomprehensible distance. Light, traveling at its maximum speed, requires 8 minutes and 20 seconds to cross from the sun's center to its surface. Yet, for all its apparent immensity, the sun is a relatively ordinary object. Its mass is roughly 2 octillion kilograms, or about 330,000 the mass of Earth. Its surface temperature hovers around 500 Kelvin, hot enough to vaporize any terrestrial material instantly, yet cooler than the atmospheres of many distant stars. The sun's luminosity, the total power it radiates across all wavelengths, amounts to approximately 386 billion megawatts. This figure is often presented without context, rendering it meaningless. A more graspable comparison. The sun radiates more energy in a single second than human civilization has consumed since the first fire was kindled. Yet even this incomprehensible output is the gas of stars. Stars burn with greater intensity. Some radiate hundreds of times more power. A few radiate thousands of times more. What made the sun measurable was not its uniqueness, but its proximity. At a distance of 150 million kilometers, the sun was close enough that its angular size in our sky was large enough to measure with reasonable precision using early telescopes. Its distance could be triangulated through parallax, the apparent shift in the sun's position of orbits, a technique that also allowed astronomers to estimate distances to other stars. Once distance was known, brightness measurements could be converted into true luminosity. Once luminosity and surface temperature were known, mass could be inferred from the relationship between these properties. The sun became measurable not because it was special, but because we lived next to it. This proximity created a cognitive distortion. For most of human history, the sun was the only star whose properties we could determine with confidence. Consequently, the sun's characteristics became unconsciously embedded in human intuition about what stars are like. We developed an implicit assumption that stars are probably somewhat like the sun, that the sun represents a typical stellar object. This assumption was not stated explicitly. It shaped thinking at a deeper level, influencing which questions seemed worth asking and which seemed absurd. The question, "Are there stars much larger than the sun?" did not strike ancient or medieval astronomers as particularly urgent, because the sun already seemed impossibly vast. The question, "Do stars have different internal structures?" seemed strange because the sun appeared to be simply a glowing sphere. The question, "What would happen if a star were 10 times more massive than the sun?" felt almost philosophical rather than scientific, because no observational method existed to test it. This perceptual anchor persisted even as observational methods improved. When early spectroscopy revealed that stars had different surface temperatures, it took decades for astronomers to recognize that temperature and size were not independent properties, that a hotter star tended to be smaller, and a cooler star tended to be larger, in ways that violated naive expectation. When calculations suggested some stars must be enormously massive, there was initial skepticism. How could such objects be real if they violated intuitions shaped by the sun? Yet the sun's role as baseline is not a historical accident or psychological peculiarity. It serves a genuine scientific function. By establishing precise measurements of solar properties, astronomers a standard against which all subsequent observations could be calibrated. The sun's spectrum became a reference spectrum. Its distance became the basis for a cosmic distance ladder. Its age, inferred from nuclear physics and evolutionary models, provided it a benchmark for understanding stellar life cycles. The sun is the only star we can observe in sufficient detail to understand its internal structure through techniques like helioseismology, the study propagating through the sun's interior, which reveals layers and processes hidden from direct view. This is the paradox underlying stellar astronomy. We must use the sun as a measuring stick to understand an object that is, in fact, unremarkable. The sun is not larger than most stars. It is smaller. Most stars in the galaxy are red dwarfs, objects less than half the sun's mass, burning with a fraction of its luminosity. The sun, in this context, is actually a relatively large and luminous object. But these truths only become apparent once we have measured other stars and compared them systematically. Until that comparison is made, the sun dominates perception, appearing supreme. Understanding this limitation is essential to the story that follows. Everything we are about to explore, the discovery of giants, the measurement of extremes, the recognition that the universe contains objects and processes far more exotic than the sun, began with the recognition that our initial baseline was incomplete. The sun showed us how to measure, but it could not tell us the full range of what stars could be. The human brain did not evolve to comprehend objects on stellar scales. Our sensory apparatus developed to navigate a world measured in meters and kilometers, distances we could walk, see across valleys, or traverse in a few days' journey. Our intuitions about size, distance, and time are calibrated to terrestrial experience. A mountain seems impossibly distant until you understand it took 3 days to reach it. A chasm seems impossibly deep until you calculate how long a stone takes to fall to the bottom. These are the natural scales of human perception, the framework within which our cognitive apparatus operates with reasonable accuracy. The Sun breaks this framework entirely. Its diameter of 1.4 million kilometers is not merely larger than terrestrial objects. Represents a category of largeness that human intuition cannot grasp directly. If you were to stand at the Sun's center, you could not walk its surface. You could not drive there in a lifetime. You could not fly there in a spacecraft with human technology. The distance light travels in mere seconds across the Sun's diameter exceeds the entire path of human civilization's greatest journeys. To truly understand this is to recognize that comprehension requires something other than intuitive grasp. It requires abstract reasoning, mathematical comparison, and the willingness to trust calculations over feeling. This cognitive limitation extends beyond mere size. The Sun's temperature presents a similar challenge. Its surface, at 5,500 Kelvin, exists in a physical regime with no human analog. The hottest temperatures humans can tolerate directly for brief periods are measured in hundreds of Kelvin. The Sun's surface is roughly 10 times hotter than boiling water. Yet even this comparison fails because boiling is a terrestrial phenomenon involving phase transitions in water. The Sun's surface is not hot the way a fire is hot. It is hot in a fundamentally different way. State of matter where atoms are ionized, where the distinction between solid and gas becomes meaningless. Energy radiates outward in forms of light invisible. The Sun's interior temperatures are even more alien to human experience. At the core, where nuclear fusion occurs, temperatures 15 million Kelvin. This is not merely hotter than anything on Earth. It exists in a physical domain where quantum effects dominate, where the very notion of temperature, as humans intuitively understand it, begins to break down. Yet even at these extremes, the Sun is not exceptional. Many stars burn hotter. Some have core temperatures exceeding 100 million Kelvin. The Sun's interior is merely the first step away from human experience toward a regime where physics operates according to laws we can write mathematically, but cannot visualize. This mismatch between human intuition and stellar reality became once astronomers began measuring other stars. If the Sun were truly typical, if the Sun represented the standard type of star, then the universe would be comprehensible by simple extrapolation. But measurements revealed something unexpected. The Sun was not a typical star. It was not even average. By mass, by luminosity, by size, the Sun occupied a particular niche within the population of stars. This realization was not dramatic. It arrived gradually through the accumulation of increasingly precise measurements. But its implications were profound. If the Sun was not typical, then the mental model built on the Sun as reference object was fundamentally incomplete. Consider what this means for the question of stellar size. The Sun appears vast. Its diameter is nearly 110 times Earth's diameter. More than 1 million Earths could fit inside the Sun's volume. These are staggering proportions. Yet once astronomers began measuring other stars, they discovered objects that dwarfed the Sun. Some were merely twice the Sun's diameter, a startling revelation that would have seemed impossible based on naked eye observation. Measurements pushed further. Some stars were 5 times the Sun's diameter, 10 times, 50 times, 100 times. With each discovery, the mental image required adjustment. The Sun, which had seemed supremely large, became small by comparison. The psychological effect of this sequence cannot be understated. Each new measurement was not merely a numerical fact. It represented a revision to the fundamental understanding of what the universe contained. If stars could be 10 times larger than the Sun, could they be 100 times larger? Could they be 1,000 times larger? The questions became progressively more speculative. Yet they were the natural consequence of recognizing that the sun was not a boundary, but merely one point along a spectrum. Each discovery opened new possibilities for what might exist. This is where the measurement of stellar luminosity becomes crucial. The sun radiates a certain amount of total power, a quantity called the solar luminosity. Once this baseline was established through full measurement, it became possible to compare all other stars to it. A star that appeared as bright as the sun, but was measured to be twice as distant, must be actually 4 times more luminous to appear equally bright. A star that appeared fainter despite being closer must be less luminous. Through careful measurements of brightness, combined with distance estimates derived from parallax, astronomers could determine the true luminosity of distant stars. What emerged from these measurements was a recognition that luminosity varied far more dramatically than size alone could explain. Some stars were only slightly less luminous than the sun despite being much smaller. This implied they must be much hotter, burning their fuel at a more intense rate per unit mass. Other stars were far more luminous than the sun yet appeared relatively cool based on their spectrum. This implied they must be vastly larger. The pieces began to fit together. Luminosity, temperature, and size were not independent properties. They were linked by the physical processes occurring inside stars. The sun's mass is the final crucial parameter establishing it as a baseline. Mass determines gravitational strength, which in turn determines internal pressure, which determines core temperature, which determines the rate of nuclear reactions. The sun's mass of approximately 30,000 Earth masses seemed incomprehensibly large. No terrestrial analog existed. Yet once measurements of other stars were made, this became context-dependent. Some stars were more massive than the sun. Many were less massive. The relationship between mass and luminosity, once mapped across many stars, revealed a deep connection. More massive stars were dramatically more luminous, burning their fuel far faster than proportional scaling would suggest. Understanding the sun's properties with precision, therefore not merely about the sun itself. It was about establishing the foundation upon which all subsequent stellar understanding would be built. Every measurement of another star implicitly compared that star to the sun. Every classification system used the sun as a reference point. Every theoretical model of stellar structure was first tested against the one star could observe in sufficient detail to understand its internal workings. The sun was not special because it was the largest or brightest or most exotic object in the universe. It was special because it was the first standard against which all others could be measured. For thousands of years, the stars remained fundamentally unknowable. Ancient astronomers, the Babylonians, the Greeks, the Islamic scholars of the medieval period could observe the positions of stars with remarkable precision. They could catalog their brightness, track their movements across seasons, and organize them into constellations. Yet despite this accumulated knowledge, the stars themselves remained abstract entities. No observer, no matter how careful or skilled, could determine whether a star was truly distant and bright, or merely close and dim. No measurement technique existed to discriminate between these possibilities. The stars were points of light, uniform in their essential nature, separated from human observers by a distance too vast to comprehend or bridge. This unknowability was not due to lack of effort or intelligence. Ancient astronomers were brilliant observers. They understood geometry and mathematics at a sophisticated level. The limitation was fundamental. Human eyes cannot resolve the angulies of stars. A star, even the brightest star in the sky, appears to the naked eye as a mathematical point with no discernible diameter. The diffraction of light through Earth's atmosphere, the twinkling that makes stars seem alive with movement, actually obscures their true appearance. All the careful observation in the world could not reveal what naked sight could not grasp. This perceptual wall created an intellectual consequence. Without the ability to measure stellar distances or sizes, astronomers could not build models of the star system that were anything more than educated guesses. Some proposed that all stars were equally distant, arranged on a celestial sphere that rotated around the Earth. Others suggested that stars occupied space at varying distances, but without measurements, this remained speculative. The question, how far away is the nearest star, had no answer based on observation. It was a question that could not even be asked in a scientifically meaningful way. Then, in the early 17th century, the telescope was invented. The device was not sophisticated by modern standards. Early telescopes were crude instruments made of hand-ground glass lenses, prone to distortion and aberration. Yet they represented a categorical break with naked-eye astronomy. For the first time, human observers could magnify celestial objects, bringing distant phenomena closer to perceptual reach. When Galileo turned a telescope toward Jupiter in 1610, he saw something that changed astronomy forever. 4 points of light orbiting the planet. These were moon satellites of Jupiter, not of the Earth. The universe suddenly contained structures that the naked eye could not resolve. Complexity existed at scales invisible without instrumental aid. Yet the telescope's impact extended beyond the discovery of individual objects. It revealed a fundamental truth about astronomical observation. Magnification could create new information. If the telescope could reveal moons around Jupiter, could it reveal the surfaces of distant stars? Could it resolve their apparent points of light into measurable disks? Astronomers pointed their telescopes at the brightest stars with this hope. What they found was disappointing at first. Even with magnification, stars remained points. They did not resolve into disks. The telescope revealed no new information about stellar size or distance. This apparent failure actually contained profound information, though it took decades to recognize. The fact that stars did not appear to resolve into disks, even under magnification, implied that they were incredibly distant. If a star were as close as Jupiter, magnification would reveal its angular diameter. The fact that magnification produced no such revelation meant that stars must be vastly more distant than the planets. This was not a direct measurement, but it was a constraint, a limit on stellar distance, based on the negative result of not seeing what theory predicted should be visible. The real breakthrough came not from trying to magnify us directly, but from decomposing their light. In the early 19th century, astronomers began using spectroscopes instruments that passed light through a prism or diffraction grating, spreading it into a rainbow of colors and revealing the pattern of bright and dark lines within that spectrum. When starlight was analyzed this way, something remarkable emerged. Each star had a unique pattern of spectral lines. These patterns were not random. They reflected the chemical composition of the star's outer layers and provided information about temperature based on the colors that dominate them. This was a revolutionary insight. Starlight was not uniform. Each photon carried encoded information about the star that emitted it. By learning to read this information, astronomers could determine properties of distant stars without ever resolving them into visible disks. A cool star had a spectrum dominated by red wavelengths and showed specific absorption lines corresponding to molecules that only exist at lower temperatures. A hot star had a spectrum tilted toward blue wavelengths and showed absorption lines corresponding to highly ionized atoms that only exist at extreme temperatures. Yet spectroscopy alone could not measure distance. A distant bright star and a nearby dim star could produce identical spectral patterns, the same colors, the same absorption lines, while appearing to differ dramatically in brightness. The ambiguity remained. Was a faint star genuinely dim, or was it simply far away? Without distance measurement, the interpretation of stellar properties remained incomplete. This created a curious inversion. The telescope had revealed the cosmos to be far more complex than naked-eye astronomy suggested. But it had also limits of what technology alone could accomplish. Measurement required both observations and theoretical reasoning to connect them. The breakthrough came from recognizing that measurement requires multiple independent pieces of information. If the brightness of a star can be measured, and if the pattern of its spectral lines can be measured, and if the assumption can be made that the star's spectrum follows physical laws that relate temperature to luminosity, then distance becomes calculable through these relationships rather than through direct observation. This was not a direct measurement in the way that a ruler measures length. It was an indirect inference based on assumptions about how the universe works. Those assumptions could be tested by applying the same technique to the sun. A star close enough could be measured independently using parallax, a technique that uses Earth's orbital motion to triangulate stellar distances. By the 20th century, this convergence had been achieved. Multiple technique parallax for nearby stars, spectroscopic analysis for distant ones, calculations of luminosity from brightness and distance, all produced consistent results. Stars were not uniform. They came in different sizes, temperatures, and luminosities. The universe was not a simple sphere of uniform stars rotating around the Earth. It was a complex structure with variation at every scale. Yet knowledge had required patience. Naked sight had been supplemented with technology, but technology alone was insufficient. Understanding emerged from the combination of observation and the careful comparison of independent measurements until they converged on reliable truth. Starlight carries a message written in a language that took centuries for humans to learn to read. When astronomers first began analyzing the light from stars through spectroscopes, they were looking at something that had been invisible to all previous generations of observers. The light itself was the same photon traveling across the vacuum of space at constant velocity. But decomposed into its component wavelengths, that light revealed hidden structure. It spoke of elements, of temperatures, of physical processes occurring in the hearts of distant furnaces of kilometers away. The mechanism behind this revelation rests on a fundamental principle of physics. Every element, when heated, emits light at specific wavelengths. Hydrogen emits at particular frequencies, helium at different frequencies, iron, oxygen, carbon. Each element has a unique fingerprint latent. When a stars glow at high temperature, they emit this light. But the light must pass through cooler layers before escaping into space. These cooler layers absorb light at the same wavelengths that the hotter layers emit. The result is a spectrum, a rainbow of light interrupted by dark lines at specific positions. These dark lines are called absorption lines, and their positions and patterns are as distinctive as a barcode, encoding information about which elements exist in the star's atmosphere. The discovery of this connection between spectral lines and chemical composition was one of the great intellectual achievements of 19th century physics. It meant that astronomers could determine what stars were made of without ever traveling to them, without ever bringing stellar material into a laboratory. A spectroscope could reveal the presence of hydrogen, helium, and dozens of other elements in a star's atmosphere. As more stars were observed, a remarkable pattern emerged. Not all stars had the same composition. Most primarily hydrogen and helium, but the proportions varied. Some showed strong lines of heavier elements. Differences were subtle but consistent, yet spectral lines revealed more than merely composition. The appearance of lines also depended critically on temperature. At low temperatures, atoms remain neutral, bound together by atoms in their outer shells. These neutral atoms produce specific patterns of absorption lines. As temperature increases, atoms become ionized electrons, are knocked loose from atoms by the intense thermal collisions. Ionized atoms produce different patterns of absorption lines than neutral atoms do. By examining which lines appear and which disappear, astronomers could determine the temperature of a star's outer layers with remarkable precision. This was a profound realization. The spectrum of a star encodes not one piece of information, but multiple pieces simultaneously. The same data that revealed composition also revealed temperature. An experienced spectroscopist could look at a spectrum and determine almost immediately whether a star was cool or hot, and what elements dominated its atmosphere. The patterns emerged clearly once astronomers knew what to look for. Cool stars showed molecular features, absorption lines from molecules like titanium oxide, which only exist at temperatures below about 1000 Kelvin. Hot showed ionized features lines from multiply ionized atoms that only exist at temperatures exceeding tens of thousands of Kelvin. From these observations came the realization that stellar temperature and color were intimately connected. This was not a new insight. Ancient astronomers had noticed that Sirius appeared blue-white while Aldebaran appeared red. But spectroscopy provided the physical explanation. Blue-white stars were hot. Red stars were cool. The color was not arbitrary or dependent on composition. It was a direct consequence of temperature operating through the laws of thermal radiation. A hot object radiates more intensely at shorter wavelengths, the blue end of the spectrum. A cool object radiates more intensely at longer wavelengths, the red end. This connection pointed toward a deeper principle. Stellar properties were not independent random variables. They were linked by physical law. A star's temperature determined its color. Temperature also determined spectral lines would appear. And it became clear, through careful analysis, that temperature also influenced luminosity. For stars of a given size, hotter stars were more luminous. A hot star of a given diameter radiated more total power than a cool star of the same diameter, because each square meter of its surface radiated more intensely. The implications extended further. If spectral lines revealed composition, and if most stars had similar composition, mostly hydrogen and helium, with small amounts of heavier elements, then the dramatic differences in stellar properties must be driven by something else. Temperature and size emerged as the primary variables. A hot, large star would be extremely luminous. A cool, small star would be dim. But what determined the temperature of a star in the first place? That was a deeper question, pointing toward the internal processes that govern stellar structure. These relationships were not derived from first principles in a theoretical manner. They were discovered empirically through the accumulation of spectral observations. Astronomers observed hundreds, then thousands of stars. They measured the brightness, the color, the spectral type of each. Gradually, patterns emerged. Stars could be organized into categories based on their spectra. The classification system that emerged later and standardized went from the hottest stars, type O, through intermediate types to the coolest stars, type M. Within each type were subtypes, allowing more precise categorization. The system was not perfect. It was based on observational convenience and historical accident rather than underlying physical principles. But it worked. It provided a way to organize the bewildering diversity of stellar properties into an orderly scheme. What made this scheme powerful was not merely that it organized observations, but that it pointed toward an underlying reality. The spectrum of a star was not an arbitrary collection of features. It was an expression of the star's fundamental physical state: temperature, composition, and density. The basic parameters describing matter in any physical context could all be inferred from spectral analysis. The star's spectrum was a kind of dimensional fingerprint, a description of its physical condition encoded in the light it emitted. Once astronomers learned to read that fingerprint, the stars to be mysterious and became comprehensible as physical objects following natural laws. In the early years of the 20th century, two astronomers working independently arrived at the same realization. Ednar Hertzsprung, a Danish observer, and Henry Norris Russell, an American theoretician, both recognized that plotting stars on a graph could reveal hidden order in stellar properties. The graph was straightforward in concept: temperature on the horizontal axis, luminosity on the vertical axis. Each star, once its temperature and total brightness had been measured, could be represented as a single point. The question was simple: what pattern would emerge? What they discovered was neither random scatter nor a simple clustering. Instead, the points arranged themselves into distinct regions. The majority of stars fell along a diagonal line running from the lower left corner cool, dim stars to the upper right corner hot, luminous stars. This diagonal band became known as the main sequence, and it would become the foundation concept for understanding stellar evolution. But the diagram revealed more than just this central trend. Other stars occupied different regions entirely. Some were hot yet dim, clustered in the lower right corner. These would later be understood as white dwarfs, the dense remnants of dead stars. Others were cool yet luminous, positioned in the upper left region. These were giants and supergiants, stars that had evolved away from the main sequence. The existence of this pattern was profound. It suggested that stars were not randomly distributed across all possible combinations of temperature and luminosity. Instead, they followed predictable pathways. A star's position on the diagram was not arbitrary. It was determined by the star's mass, age, and evolutionary stage. This single graph became a kind of cosmic map, a chart on which the entire life history of stars could be traced. The diagram did not merely organize observations. It pointed toward a deep physical truth: stars evolve. They are not static objects that remain unchanged throughout their existence. They are dynamic systems that transform over time according to comprehensible physical principles. Understanding why this pattern exists requires recognizing that a star's luminosity is not independent of its temperature. For a star on the main sequence, the relationship is remarkably tight. If you know its temperature, you can predict its luminosity with reasonable accuracy. This relationship emerges from a fundamental balance. The internal structure of a main sequence star is determined by the equilibrium between gravity pulling inward and the pressure from nuclear fusion pushing outward. More massive stars must generate higher internal pressures to support themselves against gravity. Higher internal pressures mean higher core temperatures, which means nuclear reactions and greater total luminosity. The relationship is so precise that it reflects a deep connection between mass and observable properties. Yet the diagram revealed something equally important. Main sequence stars do not occupy all possible combinations of temperature and luminosity. There is a boundary. Cool stars never reach the luminosities of hot stars of comparable temperature. This is not because cool stars are forbidden from being luminous. It is because the physics of main sequence stars prevents it. A cool star has a lower core temperature, and therefore slower nuclear reactions. To achieve the same luminosity as a hotter star, a cool star would need to be vastly larger. But if it were vastly larger, its surface temperature would increase. The relationship between mass, size, temperature, and luminosity is constrained by physical law. Stars cannot exist arbitrarily far from the main sequence without violating these constraints. The regions off the main sequence are equally revealing. White dwarfs, hot, dim objects in the lower right corner represent stars that have exhausted their nuclear fuel. Gravity has crushed the core to tremendous density, compressing a mass comparable to the Sun into a sphere the size of Earth. The star is cooling slowly, radiating away its stored heat. It is no longer supported by nuclear fusion. It is supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed indefinitely. White dwarfs are not dying stars. They are the corpses of dead stars, cooling residues of stellar remnants. The giants and supergiants occupy a different evolutionary stage. These are stars that have exhausted the hydrogen in their cores and begun fusing heavier elements. The cessation of hydrogen fusion causes the core to contract and heat. This reignition of fusion in a shell around the inert core causes the outer layers to expand enormously. The star grows in size, but its surface cools because the energy is now distributed across a vastly larger surface area. The result is a cool but extremely luminous object, a giant or supergiant, depending on how massive the star is. The diagram therefore tells us a story of stellar life cycles. A star begins on the main sequence as a young object, its position determined by its mass. As it ages and gradually exhausts its nuclear fuel, it moves away from the main sequence, tracking a path determined by its mass and the sequence of nuclear reactions occurring in its core. Eventually, it leaves the main sequence entirely, becoming a giant or supergiant. In the end, depending on its mass, it either becomes a white dwarf, a neutron star, or perhaps something more extreme. The diagram is not merely a catalogue of stellar properties. It is a chronicle of stellar evolution written in the language of physics. What makes the diagram revolutionary for the question of size is this. It provides a framework for understanding why the largest stars exist where they do. The most luminous stars are necessarily large. A star cannot be hot and dim. The physics forbids it. And the most luminous stars are not on the main sequence. They are in the giant and supergiant regions, stars that have evolved into their final phases before death. These are stars burning their fuel at catastrophic rates, expanding to enormous dimensions as their outer layers detach from the gravitational control of the core. The largest stars in the universe are not anomalies or violations of physical law. They are the natural endpoint of stellar evolution for the most massive stars. A star is a furnace in perfect balance, a system poised on the knife's edge between two opposing forces. Gravity pulls inward with relentless force, trying to compress all of the star's material toward the center. Nuclear fusion in the core pushes outward with radiation pressure, heat, and the momentum of particles ejected from reactions. The star exists in the space between these extremes, a structure that neither collapses under its own weight nor explodes outward in violent expansion. This equilibrium is not static. It is dynamic and constantly renewed, maintained moment by moment through the precise balance of these titanic forces. To understand why the largest stars exist and why they have the properties they do, we must first understand the nature of this balance and how it changes with stellar mass. The relationship between mass and internal pressure is not linear. It is exponential, a fact that profoundly shapes stellar structure. Consider two stars, one with twice the mass of another. The massive star does not simply have twice the gravitational force crushing inward. Gravity depends on the inverse square of distance. The greater mass is compressed in roughly spherical volume, which means that material in the core of the massive star experiences not twice, but many times the gravitational pressure of material in the core of the lighter star. To resist this crushing force, the core temperature of the massive star must rise dramatically. The nuclear reaction rate depends exponentially on temperature. Double the core temperature, and the reaction rate increases not twofold, but thousands of times over. This is the exponential relationship that transforms stellar structure as mass increases. The consequences of this relationship ripple outward through the entire star. A massive star must burn its nuclear fuel at a catastrophic rate simply to generate enough outward pressure to support itself. A 10 solar mass star does not burn its fuel 10 times faster than the Sun. It burns it thousands of times faster. The Sun, burning at its current rate, will remain on the main sequence for approximately 10 billion years. A 10 solar mass star will burn its fuel in perhaps 20 million years, 500 times faster for a star only 10 times more massive. The relationship between mass and lifetime is not merely a scaling factor, it is a reversal of intuition. Massive stars, which contain more fuel, burn it so rapidly that they are actually shorter lived than less massive stars. This rapid burning has a direct consequence for luminosity. A massive star must generate tremendous nuclear power to support itself. Its total luminosity, the amount of energy radiated per second, scales with stellar mass, but again not linearly. The luminosity of a main sequence star roughly scales with masses to the power of 3.5. This means that a 10 solar mass star is not times more luminous, but roughly 3,000 times more luminous than the Sun. This staggering difference emerges directly from that the star support itself against its own gravity. There is no choice in the matter. The physics dictates it. Now consider what this means for stellar size. A star's luminosity to its surface temperature and its surface area through a fundamental relationship from thermodynamics. If a star is hotter, it radiates more intensely from each square meter of its surface. If a star is larger, it has more surface area to radiate from. For a given temperature, a more luminous star must have a larger surface area. A massive star, burning at an intense rate, must be tremendously luminous. If it maintains a temperature comparable to the Sun, it must be vastly larger to that luminosity across its surface. A 10 solar mass main sequence star is typically roughly 3 times the Sun's diameter. But this is still relatively modest. The truly giant stars, hundreds or thousands of times the Sun's diameter, belong to a different category. These giants are not main sequence stars at all. They have evolved beyond the main sequence, beyond the era of hydrogen burning in their cores. When a massive star exhausts its core hydrogen, the physics changes fundamentally. The core can no longer support itself against gravity through hydrogen fusion. Gravity crushes inward, raising the temperature further. At a certain point, helium begins to fuse. This reignition of nuclear fusion releases energy, but the core structure has already been disrupted. The contraction and subsequent reignition cause the outer layers of the star to expand dramatically. The star swells to an enormous size. Why does expansion accompany the loss of hydrogen fusion in the core? The answer lies in the structure of the star's layers. The hydrogen that has been fusing resides in a shell around the inert helium core. When helium fuses, it also resides in a shell just outside the helium core. The energy from these shells flows outward, but it is no longer efficiently contained by a stable core structure. The star becomes unstable. The outer layers respond by expanding. As they expand, they cool. The star becomes a red giant, cool and vastly enlarged, yet tremendously luminous, because its large surface area radiates the enormous energy generated by the rapid burning in the core. For even more massive stars, this process repeats. Helium exhausts, carbon fuses, neon fuses, oxygen fuses. With each cycle, the core contracts slightly, the temperature rises, and the outer layers expand further. The star becomes progressively larger and cooler while remaining luminous. Eventually, after perhaps a dozen cycles of thermonuclear burning at increasing densities and temperatures, the star becomes a supergiant, an object with a radius hundreds or even thousands of times the Sun's diameter. Iron accumulates in the core, but iron cannot fuse under any conditions that occur naturally in stars. When iron reaches the core, gravity will crush the core catastrophically, triggering a supernova explosion that will destroy the star. The largest stars we observe are in these final phases for supernova. They are not objects that have been building gradually over billions of years. They are objects that have undergone rapid transformation over mere millions of years, expanding as their cores evolved through successive cycles of nuclear burning. Their enormous size is not a stable condition, but a temporary phase, a final gasp before violent death. The relationship between mass, gravity, pressure, and size has led to a single profound conclusion. The largest stars are not the oldest or the most stable. They are the most massive and the most doomed, racing toward explosive endings while expanding to their greatest dimensions. The fundamental challenge of measuring stellar sizes is difficult to state, extraordinarily difficult to solve. Stars are too far away. Even Betelgeuse, one of the nearest red supergiants and one of the brightest stars in the night sky, subtends an angular size so small that the most powerful telescopes, available through most of astronomical history, could not resolve it into a visible disk. The human eye can distinguish 2 points of light as separate only if they are separated by 1 arcminute, the width of a fingernail held at arm's length. Stars appear as points separated by many arcminutes or degrees. Betelgeuse, despite its enormous actual size, occupies an angular diameter of less than 1 arcsec, roughly 1/30th of 1 arcminute. Direct measurement of stellar disks was simply impossible with conventional telescopes. This impossibility created a methodological crisis. Astronomers could measure how bright a star appeared. They could measure its spectrum and determine its temperature. But without knowing the star's actual size, they could not fully characterize it. A dim star could be genuinely faint, or it could be distant and bright. A cool star could be genuinely cool, or it could be large and therefore radiating its total luminosity across an enormous surface, making it appear dim despite burning at high intensity in its core. The problem demanded indirect approaches methods that inferred size through reasoning rather than direct observation. The first approach relied on distance measurement combined with luminosity calculations. If a star's distance could be measured through parallax, the apparent shift in position as Earth orbits the Sun, then its true luminosity could be calculated from its apparent brightness using the inverse square law. Parallax measurements, however, were limited to relatively nearby stars. The more distant a star, the smaller its parallax shift, and the more difficult and uncertain the measurement became. Stars farther than a few hundred light-years could not be reliably measured by parallax alone, with the instruments available through the 20th century. This meant that for the vast majority of stars, particularly the distant giants and supergiants, parallax measurement was impossible. A second approach from spectroscopy. When a star rotates, its spectral lines broaden. Material on the side of the star rotating toward Earth moves at a velocity that increases the frequency of its light slightly. Material rotating away shifts the frequency downward. The combination produces a broadening of spectral lines. The faster the star rotates, the greater the broadening. If the rotational velocity is known from some other method, and the broadening is measured, then the star's radius can be calculated. A rapidly rotating star of a given radius produces more broadening than a slowly rotating star. This method provided information about stellar size, but it depended on knowing the star's rotation speed, which was often and varied unpredictably from star to star. A more direct approach came with the discovery of exoplanets and the development of transit photometry. When a planet passes in front of its host star from Earth's perspective, it blocks a small portion of the star's light. The amount of light blocked depends on planet's size relative to the star, but the transit method can work in reverse. If an object of known size passes in front of a star, the amount of light blocked reveals the star's size. In practice, astronomers could use stars as mutual transiting partners in binary systems. When one star passes in front of another, the light blocked reveals the size of the foreground star. This method was powerful, but limited to stars in close binary systems where transits actually occur from Earth's viewpoint. A small fraction of all stars. A revolutionary breakthrough came with the development of stellar interferometry. The principle on interferometry is that light waves can interfere with each other, creating patterns of constructive and destructive interference. If two telescopes are separated by a large distance and their light is combined, they can act together like a single telescope with an aperture as large as the separation between them. This greatly enhances angular resolution. By combining light from telescopes separated by tens of meters, astronomers could achieve angular resolution capable of resolving stellar disks directly for the first time. The technique was technically demanding, maintaining the precise alignment needed to combine light from widely separated telescopes required extraordinary precision, but it worked. With interferometry, astronomers could finally measure stellar diameters directly for nearby stars and bright stars. Betelgeuse was among the first targets. The measurements confirmed what theory had suggested. Betelgeuse was enormous, roughly 900 times the Sun's diameter, depending on exactly where the star was drawn and how its brightness varied across its face. Yet interferometry had limitations. It worked best for bright stars relatively close to Earth. The most distant giants, the most extreme supergiants, remained beyond its reach. The faintest stars, even if relatively nearby, were too dim for interferometric measurements. This created a paradox. The very stars that astronomers most wanted to measure, the largest, most extreme objects, were often the most difficult to observe. The largest stars tended to be distant. They also tended to be surrounded by dust and gas, remnants of their formation, and the material they were ejecting as they evolved. Dust obscured their visible light, making them visible to optical telescopes, but sometimes bright in infrared radiation. The most extreme supergiants were often embedded in dense nebulae, their light heavily reddened and attenuated by the dust between them and Earth. Moreover, not all measurements could be directly compared. Some measurements came from optical wavelengths, others from infrared. Some assumed the star was spherical and uniform in brightness, while in reality many red supergiants are markedly non-spherical, with prominent hotspots and cooler regions. Some measurements were based on models that assumed particular compositions and internal structures. When measurements from different techniques and different wavelengths were compared, they sometimes disagreed. Astronomers had to develop criteria for deciding which measurements were most reliable, which required judgment calls and careful analysis. The history of measuring stellar sizes is therefore not a simple story of progressive improvement. It is a narrative of competing techniques, conflicting data, and the gradual accumulation of evidence from multiple independent methods until convergence suggested a reliable answer. Early measurements were often wrong. Some objects thought to be single stars turned out to be binary systems. Combined light had been misinterpreted. Some size estimates were revised dramatically as new data accumulated. The largest known star changed repeatedly as improved measurements, objects even more extreme than previously measured. The recognition that stars could be vastly larger than the Sun did not arrive as a sudden revelation. It accumulated gradually through measurements that seemed increasingly implausible until they could no longer be dismissed as observational error. Betelgeuse appeared in the night sky as a point of light, like all stars. Yet by the middle of the 20th century, measurements suggested that this point of light was actually an object so enormous that if placed where the Sun is, it would extend past the orbit of Mars. Deneb, another bright star visible to the naked eye, appeared similarly vast. Aldebaran, though fainter, showed comparable dimensions. These were not exotic distant objects requiring specialized equipment to observe. They were prominent stars visible to anyone looking at the night sky. Yet they concealed within their apparent simplicity a structure of almost incomprehensible scale. The initial resistance to accepting these measurements was understandable. Common sense rebelled against them. How could an object be so large and yet visible only as a point? How could such an enormous support itself? The answers required understanding processes that operate at stellar scales and time scales profoundly different from terrestrial experience. The red supergiants are not stable objects that have existed unchanged for billions of years. They are transient phenomena, temporary configurations of matter destined to transform or catastrophically collapse within cosmically brief periods. The physical process that creates these giants begins with the exhaustion of a star's core hydrogen. For a massive star one containing at least 8 or 10 times the Sun's mass, the core hydrogen lasts only a few million years. When it is consumed, the star enters a crisis. The core, no longer supported by the outward pressure of hydrogen fusion, collapses under gravity. As it collapses, it heats. Temperature rises to levels previously unattained. At approximately 100 million Kelvin, helium begins to fuse into carbon and oxygen. This process releases energy, reigniting nuclear reactions in the core. The reignition of fusion is catastrophic for the star's structure. The sudden infusion of energy cannot be confined within the core. It propagates outward, destabilizing the layers above. The star's outer envelope responds to this disturbance by expanding. The expansion is not gradual or controlled. It is violent, rapid, and dramatic. Within thousands of years, blink in cosmic time, the star swells to dozens or hundreds of times its previous size. The surface moves outward, and as it does, it cools. The star transforms from a hot blue main sequence star into a cool red giant. This expansion is not mysterious. It follows directly from the physics of stellar structure. As the outer layers move outward, the material becomes less dense. Gravity's grip weakens with distance. The temperature drops. But the star remains luminous because energy from the fusing core is constantly flowing outward. The combination of enormous size, continued energy generation, and cool outer layers produces a star that is vastly more luminous than it was before, yet appears red rather than blue. This is the red giant phase, a predictable and inevitable stage in the evolution of massive stars. Yet, for the most massive stars, the giant phase is merely a beginning. As helium in the core is consumed, the same process repeats. The core collapses again, temperatures rise further. Carbon and oxygen begin to fuse into neon and magnesium. The core is reignited, and the outer layers expand further. The star becomes cooler. It becomes a red supergiant. For stars massive enough, this cycle continues multiple times. Neon fuses. Oxygen fuses. Each cycle's expansion, each creates an even more enormous envelope. The red supergiants observed in the night sky are products of this iterative process. Betelgeuse has undergone multiple cycles of core exhaustion and reignition. Its envelope has expanded to dimensions so vast that if it replaced the Sun at the center of our solar system, its surface would brush against the orbits of the terrestrial planets. The star is not held together by a stable equilibrium between gravity and fusion pressure, as main sequence stars are. It is in a state of dynamic imbalance, its outer layers tenaciously held by gravity, but constantly threatening to expand further or collapse inward. This state of imbalance has profound consequences. Red supergiants are inherently unstable. Their surfaces are often irregular, with prominent hotspots and cooler regions. Some red supergiants exhibit pulsations, their surface expanding and contracting rhythmically over periods of months or years. Others show evidence of mass loss, ejecting material into space at velocities of tens of kilometers per second. The star is literally its atmosphere, casting off material that will form dust clouds and nebulae around it. The red supergiant is not a finished product, but an intermediate state, a temporary configuration of matter following a trajectory toward eventual catastrophe. The recognition of this temporary nature was crucial to understanding red supergiants. 19th century astronomers, confronted with the enormous size measurements, sometimes imagined these stable objects that had somehow persisted in this configuration for billions of years. The physics something entirely different. A red supergiant cannot maintain its configuration for long. The energy generation in the core is so intense that fuel is consumed rapidly. Helium becomes exhausted. Carbon becomes exhausted. The cycles accelerate. Within a few million years at most, sometimes far less, processes that created the red supergiant will lead to its destruction. The destruction, when it comes, is violent beyond comprehension. The core, after exhausting nuclear fuel, cannot support itself. Gravity overwhelms all other forces. The core collapses catastrophically, compressing matter densities that violate everyday intuition about how physical matter behaves. The collapse is halted only when the core reaches such extreme density, quantum mechanical effects become important. At this point, the inward motion reverses. The rebounding core generates a shock wave that propagates outward through the star. Shock wave, energized by the intense release of gravitational potential energy, tears the star apart. The destruction is called a supernova, and it is bright enough to outshine an entire galaxy of billions of stars. Understanding this process was perhaps the most important intellectual achievement of 20th century astronomy. It revealed that the largest stars visible in the night sky were not ancient, stable monuments to cosmic permanence. They were dying objects, burning with feverish intensity in their final moments before explosive death. The red supergiants were not the universe at rest. They were the universe in crisis, demonstrating that nature permits extremes and instabilities alongside the orderly stability of main sequence stars like the Sun. The question of which star is largest cannot be answered with the finality one might expect from a factual inquiry. The answer changes as observational capabilities improve, as new regions of the electromagnetic spectrum become accessible, as measurement techniques are refined. For this reason, the history of the largest star is not a narrative of a single breakthrough moment, but rather a series of incremental discoveries, each revealing something larger than what was previously known, each raising the question of whether something more extreme might exist beyond the current horizon of observation. For much of the 20th century, Betelgeuse held the position of largest known star. Its enormous size was 700 to 900 times the Sun's diameter, depending on the measurement technique, and how one defined the star's edge seemed almost incomprehensibly vast. Yet measurements gradually revealed other candidates. Antares, another red supergiant visible to the naked eye, appeared to rival Betelgeuse in size. Deneb, despite fainter and farther away, showed dimensions that challenged Betelgeuse's supremacy. These were not exotic distant objects requiring specialized telescopes to observe. They were stars catalogued since antiquity, prominent in the night sky, yet their true dimensions had remained hidden until measurement techniques could resolve them. The revelation of new giants accelerated in the latter half of the 20th century, driven by improvements in astronomical instrumentation and the expansion of observation beyond visible wavelengths. Infrared astronomy proved particularly transformative. Many of the largest stars are cool objects, radiating most of their energy at infrared wavelengths invisible to human eyes and largely opaque to visible light telescopes. By observing in infrared, astronomers could detect stars completely hidden in visible light, obscured by dust clouds, or simply too dim in visible wavelengths to be easily catalogued. These infrared observations revealed a population of cool giants that had been largely unknown to classical astronomy. The discovery of NML Cygni in the 1970s exemplified this new ability. This was not a bright star visible to the naked eye. It was a cool supergiant embedded in dust, detectable only through infrared observation, and only then with careful analysis of its spectrum. Yet measurements suggested it was one of the largest stars known, rivaling or exceeding Betelgeuse in diameter. The discovery demonstrated that the largest stars were not necessarily the brightest. They were often the most obscured, hidden in stellar nurseries, or surrounded by the material they were ejecting as they evolved toward death. Following NML Cygni came other discoveries. V Canis Majoris, another extremely large red supergiant obscured by dust. Ui Scuti, a hypergiant star whose enormous rate distance made it difficult to measure precisely. Stephenson 218, a red hypergiant so distant and so heavily obscured that its properties remain uncertain even after decades of observation. Each discovery pushed outward the boundary of known stellar sizes. Each raised questions about how much larger such objects might become. Each also highlighted the role of measurement uncertainty in defining what is largest. The story of each discovery examining not merely as a progression of size records, but as an illustration of how astronomical measurement actually works in practice. Consider Ui Scuti, which held the title of largest known star for several years after its discovery in 2012. This star exists at a distance of approximately 20,000 light-years. So far, that parallax measurement of its distance is impossible with current technology. Its distance had to be inferred through other methods. Spectroscopic parallax, which compares the star's spectrum and brightness to theoretical models. Motion through the galaxy, which provides hints about its luminosity, and comparison to similar objects with more reliably known distances. These methods all carry uncertainties. When distance is uncertain, the calculation of radius becomes uncertain proportionally. Ui Scuti's radius measurements ranged from rough 1,700 to 2,400 times the Sun's radius, depending on which distance estimate was used, and how the star's photosphere was defined. The star's surface is not sharp. It fades gradually into space. Different definitions of where the star ends produce different size estimates. Different distances multiply this uncertainty. The result is not a single precise number, but a range of possibilities. Scientists, presented with uncertainty, typically report the range and acknowledge that future observations might revise the estimates significantly. The discovery of Stephenson 18 in 2019 exemplified this continuing uncertainty. This star, initially identified through infrared surveys and spectroscopic analysis, appeared to be even larger than Ui Scuti. Distance estimates placed it at roughly 19,000 light-years away, almost as distant as Ui Scuti, but in a different direction. The star was heavily obscured by dust, making direct observation difficult. Its spectrum suggested it was a cool red hypergiant, one of the most evolved, unstable objects known. Measurements suggested a radius of roughly 2,050 times the Sun's radius, though this numbered substantial uncertainty. Some analyses suggested it could be as large as 2,600 solar radii. Others argued for smaller values based on different assumptions about distance and composition. The significance of Stephenson 2-18 extended beyond its mere size. It raised a crucial question that remains unanswered. Is this genuinely the largest star known, or is it simply the largest star we have confidently measured so far? Given that the largest stars are often heavily obscured, difficult to observe, and at great distances where parallax and other direct measurements fail, it is entirely plausible that larger stars exist but remain undetected or unmeasured. Future surveys in infrared wavelengths might reveal even more extreme objects. Improved distance measurements using new space telescopes might revise estimates of known giants. The apparent record could change again. This uncertainty is not a failure of astronomy. It is an inherent feature of observing distant objects at the limits of current capability. The largest stars are also the rarest stars. They exist for only millions of years before exploding as supernovae. At any given time, only a handful might exist in the observable universe. Finding them requires surveying enormous volumes of space. Characterizing them requires observations across multiple wavelengths, careful analysis to disentangle the effects of distance, dust obscuration, and composition. The process is inherently slow and subject to revision. What emerges from this history, more nuanced than a simple progression toward larger and larger objects. The boundary of known stellar sizes has indeed expanded. The largest known star is thousands of times larger than the Sun, a dimension that strains human comprehension. Yet alongside each discovery lies acknowledgement of uncertainty, recognition that better measurements might revise current estimates, and awareness that objects large and that unusual might exist just beyond the edge of current observational reach. The search for the largest star is not a quest with a final answer, but an ongoing exploration of stellar extremes, each discovery suggesting possibilities for what might exist further out in the cosmos. At the boundary of stellar extremes, physics operates under conditions so unusual that the very concept of a star begins to blur. The largest known stars objects like Stephenson 2218 and VY Canis Majoris exist in a state that defies stable equilibrium. Their surfaces are so vast and so thin that the distinction between star and interstellar medium becomes ambiguous. The photosphere, the visible surface we observe, is so diffuse that atoms drift through it for enormous distances between collisions. The density is lower than what terrestrial laboratories classify as a vacuum. These objects remain bound together by gravity, still burning nuclear fuel in their cores, still radiating tremendous power outward. They exist in a temporary configuration, a brief episode in cosmic time, before the physical contradictions inherent in their nature lead to catastrophic transformation. Understanding why larger stars do not to exist requires grasping the competing processes that operate in the most massive stars. As stellar mass increases, the relationship between mass and luminosity becomes steeper and more extreme. A star twice as massive as another is not merely twice as luminous. The relationship scales roughly as mass to the power of 3.5. This means that tripling stellar mass increases luminosity roughly 30 times. A star massive enough to enormous, far larger than Stephenson 218, would be so luminous that its core temperature would rise to levels where nuclear reactions occur at catastrophic rates. The fuel would be consumed in millions or even hundreds of thousands of years rather than millions of years. This rapid fuel consumption has a direct consequence. The most massive stars have the shortest lifespans. A star with the mass of the Sun burns approximately 10 billion years. A star 30 times more massive burns its hydrogen, perhaps a few million years. A star 100 times more massive exhausts its fuel in mere hundreds of thousands of years. This is not merely a scaling of timescale. It represents a fundamental constraint on stellar evolution. The more massive the star, the faster it must burn, and the sooner it will exhaust the fuel that maintains its structure. Now consider what this means for stellar size. A very massive star undergoes the red supergiant phase, expanding enormous dimensions as it burns heavier elements in its core. But this expansion phase only lasts for a fraction of the star's total lifetime. For a star massive enough to become even larger than the known supergiants, this phase would last perhaps hundreds of thousands of years or less. The star would spend this brief epoch at tremendous size, then catastrophically collapse. At any given time in the observable universe, the number of ultramassive supergiants would be vanishingly small. The probability of one existing nearby enough and remaining bright enough for astronomers to detect would be low. This argument that the most extreme objects are rare because they are forbidden by physics, but because they exist for only brief cosmic moments provides a framework for understanding why a maximum stellar size rather than an unbounded distribution. Stars can be arbitrarily massive in principle. Physics does not forbid a star with 1,000 solar masses, but such an object would burn its fuel so rapidly that it would complete its entire evolution in perhaps tens of thousands of years. The observable universe is billions of years old, yet any given snapshot it captures only a single moment. The probability that we are observing an ultramassive star during its brief giance is extraordinarily low. We are far more likely to observe objects that persist for millions of years than objects that exist for only thousands. Yet this reasoning doesn't completely explain why we do not observe stars larger than those currently known. There could be selection effects at work. The largest stars are also the rarest. They tend to be distant and obscured by dust. Perhaps extremely large stars exist, but remain undiscovered simply because finding them would require searching vast volumes of space. Perhaps our current surveys have not covered the regions of the galaxy where such objects might be hiding. The incompleteness of astronomical surveys is always a consideration when discussing observational limits. Another possibility involves stellar mergers. In dense stellar environments, two stars can sometimes collide or undergo a close interaction that causes them to merge into a single object. A merged star would contain the mass of both progenitors. If massive stars merged, the result could potentially be more massive than either progenitor alone. Such a merged object might become a star larger than single stars can become through normal evolution. However, the physics of stellar mergers are poorly understood. The merger process would generate enormous quantities of energy. Much of this energy would be radiated away as stellar wind. The resulting merged object might not survive as a coherent star at all. Alternatively, it might become a cocked object, a neutron star, or black hole rather than a giant star. The outcome depends on details that remain uncertain. The concept of an upper limit on stellar size thus emerges, not as a hard boundary set by physical law, but as a soft edge determined by competing processes. There is no specific size above which a star cannot exist, but stars above a certain size are so massive and broadly that they are intrinsically rare. Their existence would be brief. Finding them would be difficult. For these reasons, they do not populate our surveys, and we have no confirmed observations of them. Yet the question remains open. Could Stephenson 2-18 or some undiscovered star actually larger than current measurements suggest? The uncertainties in distance and size estimates for the known hypergiants are substantial. A modest revision in distance estimate could significantly increase inferred radius. A discovery of an obscured hypergiant, hidden in a dense nebula, or embedded in a cluster, could reveal something even larger. The frontier of knowledge at this extreme has not been clearly demarcated. It remains a region where observation and theory meet uncertainty, where confident claims give way to qualified statements about what might exist. What becomes clear from examining the physics of extreme stars is that size and stability are inversely related. The largest stars are the least stable. They are burning their fuel at unsustainable rates. They are ejecting material into space as stellar winds. Their structure oscillates and fluctuates. Within comically brief periods, they will collapse. The largest star ever discovered is not an ancient monument to cosmic stability. It is a transient phenomenon, a brief configuration of matter destined for violent transformation. The universe does not reward size with longevity. It punishes it with instability and early death. We began this exploration with a simple question: what is the largest star in the observable universe? The journey to answer that question has carried us through centuries of astronomical discovery, through the development of measurement techniques that extended human perception its natural limits, through the construction of theoretical frameworks that revealed the invisible processes governing stellar structure, yet arriving at an answer, or rather, arriving at the acknowledgement that no final answer exists. Only the best measurements current technology allows is not the endpoint of understanding. It is an opening toward a larger comprehension, one that extends beyond the specific properties of individual stars toward an examination of these discoveries mean for human knowledge and human perspective. A star of the magnitude we have been discussing, an object 2,000 times the Sun's diameter, containing tens or even hundreds of times the Sun's mass, represents a scale of physical reality that human intuition cannot grasp directly. To render this comprehensible, we resort to comparisons and analogies, yet these comparisons invariably fail to capture the true magnitude. If the Sun were the size of a grain of sand, this supergiant would be a sphere hundreds of meters in diameter. If the Sun were reduced to the size of a marble, the supergiant would be larger than a football stadium. The Earth, world, 1,742 kilometers in diameter, an object of vast size by terrestrial standards, would be lost inside this star's volume. Millions of Earths could fit within it with room to spare. Each of these comparisons is accurate, yet none conveys the visceral sense of what such vastness truly means. Consider the star's energy output. The Sun radiates approximate 386 billion megawatts of power continuously. This is an incomprehensible quantity. All of human civilization's energy consumption across all of history amounts to a fraction of what the Sun radiates in a single second. Yet the largest supergiants radiate far more. Some burn with a luminosity thousands of times greater than the Sun. The total energy radiated by such a star in a year exceeds the total energy that human civilization has ever produced. This is not hyperbole. It is a straightforward calculation based on luminosities and known timescales. The asymmetry between human energy production and stellar energy production is so profound that it renders human power generation literally invisible at stellar scales. Yet this enormous star, vast beyond human scale, powerful beyond human attention, occupies infinitesimal fraction of the observable universe. The observable universe has a radius of approximately 46.5 billion light-years. This is the distance to the edge of the region from which light has had time to reach Earth since the moment of the Big Bang. Within this volume are hundreds of billions of galaxies, each containing hundreds of billions of stars. The largest stars known, the objects we have been examining, are perhaps 1 in a million or rarer still. Most stars are small red dwarfs, objects smaller than the Sun, burning dimly for trillions of years. The supergiant we have been discussing is exceptional, rare, brief. It occupies, in the context of the cosmos, less space than a grain of sand occupies in the Earth's oceans. This perspective holding simultaneously the recognition of the star's incomprehensible vastness and its cosmic insignificance, to understanding what the pursuit of stellar extremes reveals about the universe and about human knowledge. We began this documentary by acknowledging a fundamental human limitation. Our brains evolved to process objects on terrestrial scales, distances we could walk or see across horizons. The attempt to comprehend stellar and cosmic scales requires abandoning intuition and relying instead on measurement, calculation, and abstract reasoning. The journey we have traced from naked eye observation to spectroscopy to interferometry, astronomy, is fundamentally a journey of extending human perception through technology and theory, the boundaries of direct sensory experience. What makes this journey intellectually consequential is not that it has produced larger and larger numbers. Rather, it is that each step along the way has revealed new layers of physical reality operating according to an articulate and test. The Sun is not simply a bright object in the sky. It is a nuclear furnace, a system governed by quantum mechanics and thermodynamics. Stars are not uniform objects. They are diverse in mass, temperature, size, evolutionary stage. The largest stars are not stable ancient monuments. They are dying objects, burning with frantic intensity in their final moments before catastrophic collapse. Each of these realizations emerged not from philosophical speculation, from careful observation combined with theoretical reasoning. The methods that allowed us to understand stellar property spectroscopy, parallax measurement, interferometry reveal something profound about how human knowledge actually works. We cannot observe stellar interiors directly. We cannot measure stellar distances by simple geometric methods. Yet through ingenious techniques that connect observable properties to physical principles, we can infer what we cannot see. A spectral line is about atomic structure. A star's brightness combined with its distance tells us about its luminosity. A pattern of pulsations in a star's light tells us about its internal structure. Observation and theory combine to create knowledge that transcends direct perception. This process is not unique to astronomy. It characterizes all scientific understanding of reality beyond human scales. We cannot see atoms directly, yet we understand their structure through the patterns of light they emit and absorb. We cannot observe the center of the Earth, yet we understand its composition and temperature through the propagation of seismic waves. We cannot perceive the motion of galaxies directly, yet we measure it through the subtle shifts in spectral lines. Science is fundamentally the art of inferring what we cannot directly observe from careful measurement of what we can observe, guided by theoretical principles that connect observation to underlying reality. The discovery of the largest star ever found is thus not merely an astronomical fact, object of particular size at a particular distance. It is a demonstration of what human intelligence can achieve when it combines careful observation with mathematical reasoning and theoretical understanding. It is evidence that reality operates according to comprehensible principles, principles that hold even at scales and under conditions radically different from human experience. The largest star reminds us that the universe is not arbitrary or incomprehensible. It follows laws. It permits measurement. It yields to patient investigation.